And it is this fact which, startlingly enough, disproves Einstein's special relativity altogether.
Okay. I've been following the YouTube channel Dialect for some time now. In fact, it's part of the reason I decided to start making videos about relativity myself. I found that Dialect provides thought-provoking viewpoints and analysis with excellent visuals. But their latest video made me rub my head a little too much, so I thought it would be worthwhile to put my reaction out there. I'd love to hear other opinions as well. You can find the original video link in the description, and I will try to just skip to the interesting bits.
By now, most people have heard of the one-way speed of light problem, a strange conundrum in physics which tells us that we cannot know the actual one-way speed of a light beam.
He is of course correct, and this is really important to understand.
Given an infinite class of equivalent formalisms, how do we go about determining which one corresponds to the truth? This is Dialect with How the One-Way Speed of Light Problem Disproves Einsteinian Relativity.
Unless he's got a test to measure the one-way speed of light, this is trolling. But we'd have heard if any such test had ever been done.
At the core of Einsteinian relativity lies the crucial concept of invariant light. In a nutshell, this concept tells us that an inertial observer will always measure light to travel at speed c in their own frame of reference, regardless of that frame's speed relative to other observers. This contrasts starkly with the classical picture. The problem with the classical picture, of course, began when such anisotropic light behavior failed to turn up in observation. Numerous setups, including most famously the Michelson-Morley experiment, were designed to test for such anisotropies. In essence, designed to see whether observers in motion with respect to one another would measure different speeds for light in their frames or not. And the results they returned were always null.
Which is perfectly consistent with Einstein's theory of special relativity.
And in 1905, Einstein reinforced this idea by suggesting that invariant light was an expression of a deeper relative nature of space and time, a view which today is still held by modern physicists.
Yep, I wonder why.
But there's a simple problem with such a view, which is that experiments like the Michelson-Morley one never actually measured the speed of light in the first place, as most people are led to believe. Rather, such experiments measured a related but not equivalent quantity termed the two-way speed of light.
Dialect is absolutely correct here. Two-way speed, not one-way speed.
Meaning, since the more instantaneous or one-way speed of the light beam was never measured, such experiments left the possibility open that the outgoing light beam didn't travel at the same speed as the incoming light beam. But this in turn grants observers the freedom of assuming a wide latitude of outgoing versus incoming light speeds within such systems.
Okay, so where are you going with this?
Thus, we can see that the possibility of anisotropic light was never actually ruled out by experiment.
This is true, but does it need to be?
Of course, you might be thinking, well, gosh, instead of imprecisely measuring two-way averages using one clock, why hasn't anyone tried using two clocks to measure more instantaneous one-way speeds of light? Well, sure, that's a great idea.
It is a great idea, except
for the wee little problem that measuring the one-way speed of light turns out to be, well, impossible.
I want you to remember this bit. It's really important. It's also a nice graphic.
But there is in fact no empirical way to know whether any two spatially separated clocks are actually synchronized or not.
Dialect absolutely nails it right here. This is the whole problem with measuring the one-way speed of light.
We thus cannot sync two spatially separated clocks until we know the one-way speed of our signal. And we cannot know the one-way speed of our signal until we have synced two spatially separated clocks.
Yeah, this is the crux of the issue right here. In order to know the one-way speed, you have to make some assumptions about how to synchronize your clocks, which is assuming a certain reference frame of simultaneity.
This circularity demonstrates that the one-way speed of light problem isn't just some fluke of insufficiently thought-out experimentation. Rather, it's a fundamental uncertainty principle, a pivotal point of incompleteness baked into our epistemological framework.
Baked into. Here, Dialect is starting their propaganda, or they're being intentionally inflammatory.
That is, you're probably used to hearing that Einsteinian relativity is one of the most well-proven theories in all history.
It is.
But in fact, it's never been proven at all, because its central postulate, the invariance of light postulate, is empirically unverifiable.
Here, I think he's being inflammatory on purpose, or semantically argumentative.
Meaning, there's no way to know whether or not light always travels at speed c in each and every observer's frame.
Right, but do we need to know the one-way speed of light? I mean, you already said that
measuring the one-way speed of light turns out to be, well, impossible. Indeed, Einstein, confronted by the empirical result that the two-way speed of light always equals c, sought to explain it by postulating that the one-way speed of light must also always equal c.
Yes, that was the definition.
Or in other words, Einstein claimed that the physical reality of how a light beam actually moves through space in any observer's frame should be equated to a two-way averaging of that movement, regardless of the context of the motion of the observer.
Right, so the averaging of the two-way speed is a consequence also of Einstein's first postulate, which was that the laws of physics are the same in all reference frames. Any other definition of the one-way speed doesn't hold to that.
To justify this, Einstein asserted in his 1905 paper that he believed that time could not be defined at all unless a given frame's spatially separated clocks were synchronized via assuming inbound and outbound light speeds to be the same.
Again, he did this to preserve the laws of physics across all reference frames. So here's where I start to wonder what Dialect's endgame is. He's taken some pot shots at Einstein, which may just be trolling for clicks, or does he have a new theory that he thinks is better? And if so, when are we going to find out what that theory is? Now, Dialect does do a really good job here of explaining the problem of the notion of simultaneity and why it's so confusing for people who are first trying to learn relativity. So I recommend this part of the video a lot. It's really good.
Instead, you may assign them a whole range of coordinates based on whatever values you choose to assume for rightward versus leftward traveling light.
Note that he said, what you assume. He's just making a different definition than Einstein. But also notice that if you choose a speed for one direction, you have to adjust the opposite direction to compensate the two-way speed. They're always linked.
Ergo, by altering your notion of light behavior in your frame, you also alter your notion of whether any two given world events are simultaneous or not.
Key point here. Changing the one-way speed of light changes your notion of simultaneity. I get into this in my own explanation videos because it is one of the things that causes the most confusion. When you force your sense of simultaneity onto other observers, even in your own frame, you're doing so by some convention. This is something we all naturally try to do because of our innate Euclidean mindset. But I don't think we should be forcing relativity into one convention of simultaneity or another. We should be trying to find new intuitions about how time works that transcend notions of simultaneity.
This is called the conventionality of simultaneity. Not to be confused with the closely related concept known as the relativity of simultaneity.
which Dialect does a great job of explaining here, so I recommend you watch this part on your own.
Hence, you and the other observers' notions of simultaneity are said to be relative.
Great graphic here, too.
Of course, if we move beyond the restrictive scope of Einsteinian thinking,
and he ruined it. More propaganda. Or trolling.
Then thanks to the conventionality of simultaneity, you as an observer can simply choose to adopt a new light behavior convention.
You can choose to adopt a different convention, but why would you?
And in this manner, align your notion of what is or isn't simultaneous to match the other observers.
Yeah, but there will be consequences.
How could the laws of physics possibly remain unchanged if one goes about changing their simultaneity convention?
How indeed?
Well, the key lies in the coordinate transformations that govern how different frames of reference map into one another.
Coordinate transformation. Sure, you can do a coordinate transformation on anything you want. It's not a change to the theory, just a different mathematical description. We can also translate and scale space-time mathematically, but it's totally arbitrary. There is no origin of the universe labeled 0000, we just pick one by convention. Scale is just a matter of units. You can transform it all you want, but you're not actually changing anything.
That is, in Einstein's isotropic invariant light theory, the laws of physics take the same special form in every frame of reference.
Yeah, this is one of the primary features of Einstein's conventions that make it so useful. It's the simplest formulation, where you don't need to rewrite all your formulas to depend on your reference frame. It's totally practical.
But such physics only holds if you use the Lorentz transformations to go between those frames.
Right.
In an anisotropic light theory, on the other hand, the laws of physics may take an altered form, but so too will the transformation rules required to go between frames be altered.
I don't know, man. That sounds like a lot of work.
Thus, though the laws of physics change in each different theory, such changes are always compensated by a corresponding change in the transformation rules.
Yeah, it's a lot of work.
Such that the total mathematics remains consistent.
Consistent with Einstein.
And it is this fact which, startlingly enough, disproves Einstein's special relativity altogether.
Okay.
How so? Well, it's because the theory of special relativity asserts that relativistic phenomena, like clock dilation, length contraction, or mass-energy equivalence, don't have physical or mechanistic origins, but are rather ultimately only a consequence of the unique space and time geometry that is encoded via special relativity's signature Lorentz transformation. But the Lorentz transformation isn't unique. It's only one among a number of space and time geometries we can choose, which will still give us the right answers.
Okay, is he claiming that a coordinate transformation of the Lorentz transform is a mathematically unique thing? Or is he proposing a new theory here?
Put another way, special relativity asserts that all relativistic phenomena are a direct consequence of invariant isotropic light. But since each and every anisotropic theory also predicts these exact same phenomena, it would be just as valid to assert that they are a consequence of non-invariant or anisotropic light, as it would be to assert that they are a consequence of invariant light.
Okay, this sounds like a really petty semantic argument. An anisotropic coordinate transform of the isotropic formulation of special relativity is not a new theory. It's like looking at a cow through a kaleidoscope and claiming you found a new species.
Now, since Einstein's theory makes precisely such an assertion,
Well,
i.e. that its spatiotemporal geometry is both necessary and unique, it is thereby disproven by the existence of valid alternative formulations.
okay, first, The uniqueness of Einstein's formulation is not the interesting part that anyone will ever care about being disproven. The consequent geometry of the universe is what is interesting. Finding it isn't unique in making these predictions is not really that important, and disproves only a claim of uniqueness, not the usefulness of the theory. Second, are these anisotropic theories really unique, or are they just reformulations of the Lorentz transform using different conventions? I have a hunch.
Now, what it doesn't prove is whether light behavior is truly physically invariant in all frames of reference or not. As empirically, this is again impossible to prove or disprove.
Right. It's impossible to prove. So then why are we doing coordinate transforms if they don't predict different observations? Do you have a new theory with unique predictions?
But what precisely are all the possible theories? Well, let's go ahead and list them now. First, of course, we have the modern theory that light is both isotropic and invariant in all inertial frames of reference.
Right. Einstein's special relativity. Great.
Next, we have the class of Reichenbachian theories. These theories are governed by a corresponding class of transformations.
Okay, let's look at this. Now, looking at the formula, it's pretty easy to see that it's the same as the Lorentz transform, but with an additional term of b over c. If b equals 0, it just reduces down to the Lorentz transforms. No different. So what does b do? Well, it's an arbitrary parameter that lets us shift our plane of simultaneity. It effectively shears the diagram in time. Why would we do this? Well, so we can adjust our notion of simultaneity while maintaining a one-way speed of light that is invariant to frame of reference, but now anisotropic. But how do we know which value of b is correct if
measuring the one-way speed of light turns out to be, well, impossible?
Well, we can't. We cannot measure b. We cannot theorize a value for b from first principles. It's just an unnecessary parameterization of Lorentz. It is neither unique nor verifiable. It's just arbitrary.
After that, we have the class of Sexl-Mansourian theories, which leads to a much more general class of transformations.
Okay, what is all this algebra nonsense here, you're wondering? It's from Anderson's paper that Dialect gives in his description. It's just Lorentz formulations with some more parameters which do a couple things. First, it adds a clock synchronization term. Kappa here is the synchrony vector for 3D space. If you want to use this formulation in practice, you not only need to know the preferred isotropic frame, you need to know the corresponding transformations for all of the laws of physics. You also need to synchronize your clocks with that frame, and then you'd have to carry around your normal clock and your synchronized clock to do all your calculations. Now, Dialect doesn't get into this, but Sexl and Mansouri proposed a generalized class of transformations that do not assume the same geometry as Einstein. It takes this form. The epsilon term here is based on a clock synchronization method, which is chosen by convention. The a and b terms are functions of relative velocity to a preferred reference frame and are the important difference. It is a more general theory intended to test special relativity. A and b can be determined empirically, and as of now, all tests show they take values such that the equations reduce to, you guessed it, Lorentz transformations. Why did Dialect leave this out, I wonder?
And it is governed by this transformation.
Okay, this we can easily pop into Desmos. What is it? It is the same as the Reichenbach formulas in the special case where b is equal to the negative velocity. What does it do? It gives us a transformation that maps spacetime to a preferred notion of simultaneity. As we change reference frames, everything is forced to remain on the same horizontal axes, but they squish for time dilation. Is it a new theory? No. This is just a mathematical remapping of Lorentz. Just like I can map y equals x to y equals x squared. It's just a coordinate transformation. But since I have to transform all of the laws of physics to match this new clock synchronization method, nothing really changes other than the math. Lorentz is still in there, just obscured by a forced, arbitrary notion of simultaneity. I will repeat myself. We need to transcend the idea of simultaneity. This coordinate system does have some nice features, though.
And there are no weird symmetries or twin paradoxes to deal with.
Well, kinda. I've drawn the twin paradox journey on here, and if we transform to the frame of reference at the end of the journey, we see the length of the journey matches the correct twin proper time. But this is only true for constant speed journeys. If one twin goes zipping around at different speeds, it loses this nice feature and you still have to calculate it all, same as you do with the normal Lorentz transforms. So these other theories, so far, predict the same thing as special relativity because they have Lorentz baked into them. They're not fundamentally different, just Lorentz transforms with extra parameters and steps that all reduce down.
Now, there is still yet a further class of theories, because we must remember that how we assign coordinates is ultimately up to us.
Yeah, he's admitting it's arbitrary.
That just sounds like Lorentz with extra steps!
It generates a further class of theories, from out of which we can pluck a particular theory, the classical theory, which features the good old Galilean transformations.
Wait, where's the math for this? Is it just another forced transformation? I mean, sure, we can use Euclidean math. You just need these here Lorentz transforms to correct all the laws of physics. Et voila. This is where this video completely lost the plot for me. This is a wild assertion that requires a lot of mathematical gymnastics, and he just animates over it.
But you yada-yada over the best part.
Well, this is where you have to ask yourself what you ultimately believe about what it means to do science.
So here's where he waxes philosophical. I'm all for challenging the standard interpretations. In fact, it is often the standard interpretations of relativity that make it so confusing. We need to find new ways of creating intuition about space-time relativity so we can understand it more deeply. I have enjoyed many of Dialect's early videos because he's got a great way of inspiring thinking along those lines. But here, he's either doing a bit of trolling for clicks or is heading somewhere, but I don't know where. The takeaway from this video, I hope you don't have the takeaway from this video that we should replace Einstein's convention of isotropy for anisotropy in some preferred reference frame with special clock synchronizations. That would be just replacing a nice symmetric convention with an arbitrary asymmetric one, and we would get nothing for it. The correct takeaway is that the one-way speed of light doesn't matter. Here's a quote from Anderson's paper. No experiment, then, is a one-way experiment. An empirical test of any property of the one-way speed of light is not possible. Such quantities as the one-way speed of light are irreducibly conventional in nature, and recognizing this aspect is to recognize a profound feature of nature. In particular, it is a matter of principle that one cannot test for the isotropy of the speed of light, for to achieve this would be to contradict the synchrony dependencies of a one-way speed. Rather, the insights afforded by the existence of this freedom in coordinate choice are valuable in all contexts. Whether the one-way speed of light is isotropic or anisotropic is irrelevant because
measuring the one-way speed of light turns out to be, well, impossible.
We can use either isotropic or anisotropic conventions, but it doesn't change the fundamental geometric relation of space and time. Using a coordinate transformation to change simultaneity conventions is not a unique formulation of special relativity, so nothing is disproven. Special relativity is still perfectly correct. Please stay tuned on my channel. Shortly, I will release 2 videos on time dilation and length contraction specifically. My goal is to help explain those concepts in a way that demystifies some of the bad explanations while helping create some more useful intuition about how relativity works. If you have any questions in particular you'd like me to address in those videos, let me know in the comments now. I'm curious what you think of Dialect's video and my reaction to it. Also, be sure to subscribe so you don't miss a video.